individual.
Video picks up where the B tracks test to the testing screen. So step onto the plate, 20-second trials that begin and end viability. Support buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part, and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small.
I'm monitoring and get a better dynamic cross of your averages, for instance.
Selectivation, if we can manipulate that some.
Physical performance is an ergonomic handheld rest feedback and training is planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this slide, I also want to show you
without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까? 언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
In this video, you will learn.
Press the modified test you are conducting on an individual.
Video picks up where the B tracks test to the testing screen. So step onto the plate, 20-second trials that begin and end viability. Support buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part, and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small.
I'm monitoring and get a better dynamic cross of your averages, for instance.
Selectivation, if we can manipulate that some.
Physical performance is an ergonomic handheld rest feedback and training is planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this slide, I also want to show you
without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
날 좋아한다고.
언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B tracks test to the testing screen. So step onto the plate 20-second trials that begin and end viability. Port buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Activation. If we can manipulate that somehow.
Physical performance is an ergonomic handheld rest feedback and training is planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs are is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this slide, I also want to show you the
Without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
라라라라 날 좋아한다고.
언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B tracks test to the testing screen. So step onto the plate 20-second trials that begin and end viability. Port buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Activation. If we can manipulate that somehow.
Physical performance is an ergonomic handheld rest feedback and training planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs are is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this slide, I also want to show you the
without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
라라라라 날 좋아한다고
언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B tracks test to the testing screen. So step onto the plate, 20-second trials that begin and end liability. Support buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Selectivation. If we can manipulate that sound.
Physical performance is an ergonomic handheld rest feedback and training planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs are is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this slide, I also want to show you the
Without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
라라라라 날 좋아한다고
언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B tracks test to the testing screen. So step onto the plate, 20-second trials that begin and end liability. Support buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Selectivation. If we can manipulate that somehow.
Physical performance is an ergonomic handheld rest feedback and training is planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs are is very similar with humidity drips out of the device. With the app, the feedback looks a little different. On this I also want to show you the
without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
라라라라 날 좋아한다고
언젠가 우리 같이 뛸 수 있도록 Let's sweat, be happy 포카리 스웨트
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B-tracks test to the testing screen. To step onto the plate, 20-second trials that begin and end liability. Port buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Selectivation. If we can manipulate that somehow.
Physical performance is an ergonomic handheld rest feedback and training is planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs are is very similar with humidity drips out of the device. With the app, the feedback looks a little different. On this I also want to show you the
without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
라라라라 날 좋아한다고
언젠가 우리 같이 뛸 수 있도록 Let's sweat, be happy 포카리 스웨트
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B tracks test to the testing screen. So step onto the plate 20-second trials that begin and end viability. Port buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
Works and how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Selectivation. If we can manipulate that somehow.
Physical performance is an ergonomic handheld rest feedback and training is planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs are is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this I also want to show you the
without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
라라라라 날 좋아한다고
언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B tracks test to the testing screen. So step onto the plate 20-second trials that begin and end viability. Port buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
Works and how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Selectivation. If we can manipulate that somehow.
Physical performance is an ergonomic handheld rest feedback and training is planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs are is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this I also want to show you the
without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
라라라라 날 좋아한다고
언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B tracks test to the testing screen. So step onto the plate, 20-second trials that begin and end viability. Port buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work. Good job. Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Activation. If we can manipulate that sound.
Physical performance is an ergonomic handheld rest feedback and training planned and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs are is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this I also want to show you the
Without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
라라라라 날 좋아한다고
언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B tracks test to the testing screen. So step onto the plate, 20-second trials that begin and end viability. Port buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work. Good job. Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Activation. If we can manipulate that sound.
wires all over our bodies and really kind of seeing where performance can be taken to the next level.
Works and how my lungs work. Good job. Within a few minutes, we're seeing changes.
Small
By monitoring and get a better dynamic cross of your averages, for instance.
Selectivation, if we can manipulate that some.
Physical performance is an ergonomic handheld rest feedback and training implant and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs are is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this I also want to show you
without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
라라라라 날 좋아한다고
언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
지금 여기 룸 1은 영어로 진행되는 룸이어서 영어를 주 메인 언어로 사용하도록 하겠습니다. 반대로 룸 2는 한국말로 주로 사용되는 룸이고요. 그리고 대부분의 발표자님들도 한국말로 발표를 하실 것으로 됩니다. Ladies and gentlemen, as we are about to begin, please be seated. And I have a few housekeeping notes to make before we begin today's program. First, I would like to seek your cooperation in completing this seminar. Kindly switch your mobile phones to silent mode to avoid interruption. Thank you for your kind cooperation and attention. Our first seminar program will start at 3. So we have about 5 minutes. So we will meet you up at 3. Thank you. 네, 누워서 Good afternoon. It is my huge pleasure to be a moderator for this seminar in this beautiful Jeju Island. I'm Youngmin Park from Incheon National University. On behalf of Academic Committee of Korean Society of Exercise Physiology, I would like to extend a very warm welcome to all of you in this 2021 International Conference. We appreciate you taking time off your busy schedules to join us today. Our program has lined up lots of good lectures with great presenters, including professors from Japan, United States, and Korea. Please enjoy our program, and we hope you will learn a lot today. Let me briefly explain our program today. Our first session, Symposium 1, will be held at 3. And right next to that, we'll have e-poster session at 5. But this session will be held all day during a day. So you can come to the right next to the room 1. There will be a monitor and computer is already set up, so you can come and see all the posters anytime. And next, our keynote lecture will be held at 6. Let me introduce our Symposium 1. Our chair will be Ji-Seok Kim, Gyeongsang National University, and Ho-Jun Lee, Seoul Women's University. Please give them a big applause. Thank you.
Thank you, Dr. Park. I'm Dr. Ji-Seok Kim from Gyeongsang National University. This guy is Dr. Ho-Jun Lee from Seoul Women's University. In this session will be conducted in English, and the topic of this session is exercise and musculoskeletal system. Then let's start the symposium number 1, and I want to introduce our first speaker, Dr. Chung-Hoon Kang from Inha University. And he finished his bachelor's course at Sungkyunkwan University, and he received his master's degree at Sungkyunkwan University as well in exercise physiology. And he also received another master's degree at Chungbuk National University in biochemistry and molecular biology. And then he accomplished his PhD in exercise physiology at the University of Wisconsin-Madison. And then after working as a research faculty at the University of Minnesota, Twin Cities, now he is currently working as an associate professor at Inha University. Please welcome Dr. Kang Chung-Hoon.
준비하는 동안에 한국말 인사 한번 드리겠습니다. 여러 가지 준비해 주셨고 소개해 주셔서 감사드리고요. 좀 부족한데 발표하게 돼가지고 너무 영광스럽습니다. Hello everyone. My name is Chong-eun. My last name is K-A-N-G from the Inha University in Incheon, South Korea. First of all, I appreciate you inviting me to such a nice conference, 2022 International Conference of Korean Society of Access Physiology. Thanks again for having me here. Today I'm going to talk about the exercise strategies against ultrafine particles called particulate matter 2.5 in patients with metabolic syndrome who need to exercise regularly. So first, before getting started, I'd like to introduce what the particulate matter is and what the characteristics of particulate matter. So as you know, the particulate matter is really small size of molecules spreading out the atmosphere. So its diameter is equal to or less than the 2.5 micrometers. So as you can see here, according to the World Health Organization, WHO, the recommended appropriate concentration of particulate matter is equal or less than 5.0 microgram per cubic meters. However, as you can see here, the level in Korea, the level is at least 4 times higher than the level that recommended WHO. So that is a problem. And next, as you can see here, there is the increased premature mortality due to the exposure to the fine dust. So the increased number of people who died when exposed to the particulate matter, almost we predict that 7 million premature deaths occurs. And also, other research predicted that in the 2060s, the PM 2.5 exposure death rate is at least 5 times more than that levels happen in caused by the COVID-19. So that is serious. That is a problem. So as you know, the particulate matter, fine dust actually affect our physiological systems, like it hurts our brain systems. So I'm not going to talk all of it, but anyway, it also hurts the respiratory, the damage effect on the cardiovascular systems and also reproductive systems. So today I'm going to narrow down the topics in order to talk about the patient who are suffering with diabetes or hypertension. So here, when the people exposed to the particulate matter, the increased cases of hypertension or diabetes. So we started our research from being aware of this incident. So in the world, let me briefly introduce what they are doing now in the USA and Sweden, and India, China, and Germany. So they currently focusing on the PM exposure studies by using of mostly cells or animals. So that is a problem because we are more interested in the area of human. But most studies in the world, I would say that 99%, more than 90% are focused on the cells or animals. And also, another problem is that they also use the method, for example, inject particulate matters to the animals by means of, for example, the injection, not the breathing in and out, inhalation. So in case of injection studies, the problem is usually the level of the concentration of particulate matter is at least 10 times more than the physiological ranges. So we usually recommend to the inhalation studies for the PM, how the PM affects our bodies. So our research is the first to conduct exercise-induced PM inhalation studies. So we started our studies by addressing this point. For example, in the case of diabetics or hypertension patients, they have to exercise regularly. I would say that at least 4 or 5 times a week, and at least more than 30 minutes every day. So here is some guidelines which was recommended by the American College of Sports Medicine. For example, for the diabetic patient, they should perform at least 150 minutes of moderate. So I think you're an expert. I'm not going to explain all of that. And also hypertension patient, they need aerobic exercise at least 4 to 6 days every week with intensity of 40 to 60% of VO2 max, right? However, under the particulate matter atmosphere, should we exercise? They require exercise regularly. They need regular exercise every day. But under the particulate matter situations, should we recommend them to exercise? Still don't know because of the lacking of the evidence and then no any proof from any journal. Right? So today I'm going to talk about how we can how can we recommend them. Sorry. So any recommendations and or any guidelines for their exercise, for example, the frequencies, intensity, type, and time, right? So not only using the animal cell culture studies, we also have the human subject to test their lung systems and also the non-invasive way by collecting the condensate here using the R tube. So, however, we haven't realized that there are some limitations so far because mostly, as I mentioned before earlier, most research study has narrowed it down to the cellular levels. So we could not find enough data. And also, there is a lack of biomarkers. So we developed large group cohort-based studies, and they're trying to elucidate the validation of evaluation clinical indicators. And also trying to find out some proteins which is related to the metabolic syndrome following the PM exposures. So let me briefly show you what we have done so far. So we actually got the 2 different groups, the single exercise groups, also at least 1 week or up to the 12 weeks exercise group. So here, the example of a single part of exercise. So we first tested whether or not the particulate matters affect the mitochondrial functions by using seahorse. The particulate matter treatment lowered mitochondrial functions. As you can see here, there was a decreased level of maximum oxygen respiratory levels. And also we got the animal models which elicit fluorescence probe. Here, can you see the red fluorescence here? So here, the more red color, red fluorescence images indicate that there was increased reactive oxygen species stress or mitochondrial autophagy process. So we found that the PM actually elevated the mitochondrial stress by eliciting more reactive oxygen levels here. So now, then we move on to the next studies by sequencing securing the specific designed mouse chambers. Here, the particle matters generation chambers here. So we had mouse run on this treadmill. So while they're running on this treadmill, we injected particle matter inside these chambers. So we had 2 patients for this equipment, and as you can see here, Byung-hun and So Byung-hun 박사님, and 박진환 박사과정 학생이고요. 박진환 PhD student studied how aerobic exercise affect oxidative stress and inflammatory responses during particle matter exposure in specifically mouse lungs. So what they did first here is they injected particular matters into their lungs, and then we thought that there would be the 2 different ways because we can see the increase of inflammatory responses following the exposure to the particular matters. But we thought that the reason was exposed to the particular matter actually triggered inflammatory responses. Then the circulatory effect triggered the downstream pathways in the muscle tissues or kidney or liver. However, here we got the liver and the kidney tissues, and after injecting the PM tissues to the lung, we found that fluorescence tagged particular matters found in the peripheral tissues, meaning that such a smaller substance penetrated into the tissues here. So that was also problem. Then we move on to the next research topics, whether or not particular matters has any effect on the mitochondrial homeostasis. So by using the live cell confocal images, we found that PM, particular matter, also decreased the mitochondrial membrane potential here. Then we specifically designed, generated the transgenic mouse, eliciting the red fluorescence colors when their mitophage or oxidative stress increased. So we got basically 4 different groups, control and the particular inhalation groups here, and particular inhalation and exercise group and exercise only groups here. So as you can see in this graph, there was a lot bump in the percentage of the fluorescence signals in the particular matters inhalation groups, meaning that the mitochondrial homeostasis was disrupted by the particular matters. We found the several changes of the protein levels, but especially I would like to introduce this Western blot result. So same groups here, and then first we thought that PM will increase oxidative stress, and exercise-induced hyperventilation of PM worsen the oxidative stress more. However, here, as we predicted, there was increased level of oxidative stress, but exercise reversed the level of found in particular matter induced in oxidative stress. That was what we didn't expect. Then we move to the next topics, whether or not the PM affect inflammatory cytokines. So there was no changes of COX-2, but here the interleukin-6 and TNF-alpha was elevated but reversed by the exercise here. Also, the similar pattern is observed for the lung fibrosis. We stain that by using of H&E and Besson trichome method. So there was elevated level of fibrosis in the PI, but exercise reversed again. Or a similar pattern you can see here. So we also assessed the apoptosis levels in the lung by the tunnel assay. So we got the several different protein levels here, BCL2, PAX. But here, in graph B, you can see the increased level of apoptosis in the PI only groups, but the level was decreased again when they exercise. So that was interesting. So here is the conclusion. So when we tested using the lung cell lines, there was increased level of reactive oxygen species, but also the decreased cell viabilities when we treated it with particular methods. And also when we tested it using the in vivo model, here the apoptosis or inflammatory responses has been increased but reversed by the exercise. So here are the next step we are planning. So currently we are having the, for example, long-term exercise groups, for example, 12 weeks and also more than 12 weeks running groups. And by using long-term exercise, aerobic exercise groups, we are now screening their gene expressions using the transcriptome profiling and proteomic profiling. So we are trying to find out any proteins related to the particular method. Okay? And also, using the human cohort, we have several different groups in the field, and then now they're collecting their blood condensate and analyzing their inflammatory responses. This is a sort of the non-invasive method studies. So we are using the exhaled blood condensate test and the exhaled nitric oxide test. And also we are doing the broad correction and then doing the analysis of inflammatory factors like interleukin 6 or interleukin 1 better. So what is next? So we are now actively collecting the data from the animal cells and humans. Then we are hoping to develop applications for the patient with hypertension and diabetes. Because, as you know, they need to exercise almost every day. So, for example, here, so what we are recommending for them is they need to exercise, for example, the 40 or 50, more than 40, 50% of their HL max. But when the PM level is high, based on our findings, we would suggest you need to exercise certain with certain levels of exercise intensity and exercise duration here. And in case of really higher concentration of PM outside, we would suggest any alternative exercise type. That is our plan. So we cannot do that without collecting any evidence. So now as we introduced here, we are now conducting the data collections from the humans. So based on the findings, we developing these applications. So we aim to establish the healthcare system that respond to the fine dust And also hope to improve health and the quality of life through the regular exercise. So our data was generated from our facilities. You can see here. And we have website, and I appreciate that you visit us, our website, and leave any comment or feedback. And I also, I'm very lucky to have these guys because Dr. Sabe in there, and one of the postdoc here, and 소병훈, 장준호, 박진환, 이광규, 윤동진, 윤원주, 오승화, 황지영. Thanks for their effort, and then they really actively participate in the research I'm talking today. Thanks for listening, Mike. Thank you very much.
Thank you. Thank you for insightful presentation, Dr. Kang. If you have any question on the floor, please raise up your hand, and we have a microphone to share. Then I have a question. I have a quick question. Do we have any pre-treatment effect of aerobic exercise on the prevention of the down-regulation of the lung function by the ultrafine particles?
So was that your question? If we trained animal first, and then the follow step is to expose them to the particular matter, right?
Yeah, exactly.
Yeah, we got the actually 8 weeks aerobic training groups, and then we expose them to the particular matters. So what we found was the endurance exercise groups actually has more protective roles, but should be the tissue dependent. So still we are working on it. But in case of a lung, definitely there is a protective role when you do the exercise regularly. Yeah.
All right, thank you.
Yeah.
I have one more quick question. Then does it still affect the vascular function as well?
Vascular function.
Yes.
In order to do that, I need to ask Professor Kim, and also Professor Lee Se-won in Incheon University. Inha University is my university because they educate and they are the expert in it. So I would be happy if you give us any recommendation or feedback.
All right,
but still haven't tested yet.
Okay.
Yeah.
Okay. Right. If you have any question, do you have a question on the floor?
Yeah, I have one. I'm from International University, Youngmin Park. I have a quick question about I'm wondering what would be the underlying mechanism by which during the exercise mouse will inhale more particulate matters. But exercise can reduce the inflammation or the ROS, things like that. So what would be the mechanism of it?
So when we do the proteomics analysis and the transcriptome analysis, one of the possible scenario is actually we got the proteins such as the cestrin-2 bumped. So actually the cestrin-2 has been known as antioxidant roles. And also there was some regulatory domains for upregulation of those kind of proteins. So we hypothesize that the cestrin-2 is upregulated by particular matters and resulting in has protective roles for the fine dust. So that is one of the mechanisms. But I cannot continue to talk about it because we are now making the stories. probably I will be happy if you invite me next time again after we publish it.
Okay, thank you.
Thank you, Dr. Kang. Please give him a big hands again. Now, next presenter is Dr. Kwak Tong Min from Hanyang University, Eureka campus. He received a doctoral degree from University of Minnesota, and then he did a postdoctorate associate, both in Minnesota University and Boston University, Massachusetts. He is now currently as an assistant professor of exercise physiology. Today's topic he's going to address is frailty, sarcopenia, and aging skeletal muscle. Let's give him a welcome hands.
Thank you for the kind introduction, Dr. Ho-Jun Lee. First of all, it is my honor to have this opportunity at Korean Society of Exercise Physiology. This is Dongmin Kwak. I'm currently working as assistant professor in the Division of Sports Science at Hanyang University. Topic for today is frailty, sarcopenia, and aging skeletal muscle. My long-term research topic is aging and frailty to improve muscle function and quality of life. Why should we be interested in this topic? The answer is quality of life, because aging and frailty resulted in decreased muscle size, strength, and power, and increased loss of lean muscle mass, and difficulty in weight-bearing tasks, and risk of fall injury and fracture. These all factors lead to a decreased quality of life and also contribute to disability, dependence, mobility, and mortality. As we know, cardiovascular disease, osteoporosis, diabetes, obesity also can contribute these poor outcomes. Goal of the presentations are, that means after my presentation, what we need to know, the first, we needed to understand what is the best criteria for a mouse frailty phenotype. That consider heavy body weight, endurance, walking speed, strength, and physical activity. Second, we need to understand how the mouse frailty phenotype identifies the onset and prevalence of frailty across the lifespan. Third, we need to identify how the mouse frailty phenotype predicts mortality. Last, we need to understand how sex influences frailty status. These figures show the number of publications for human and frailty and mouse and frailty in the past 2 decades from PubMed. As you can see, the number of publications drastically increased from 2000 to 2020. This indicates that frailty studies are very important for all the population. Now, scientists try to understand the mechanism underlying frailty using mouse model. As I show in the previous slide, investigation of frailty in human population have drastically increased for the past 2 decades. However, the underlying mechanisms contributing to frailty are still unknown. It is likely skeletal muscle play an important role. The one important step is the identification of frailty. Fried and colleagues published a landmark paper in 2001 using the human frailty phenotype to identify individuals who were frail, intermediate frail, and non-frail. This schematic shows the human shows the human frailty phenotype by Fried and colleagues. Oh, sorry. To identify frailty, there are 5 criteria, including weight loss, exhaustion, weakness, slow walking, and low physical activity. An individual was evaluated for these 5 assessments, and if an individual fell below the value in 3 or more, the individual was identified as frail. If the individual fell below the cutoff value in 2 of the markers, the individual was identified as intermediate frail. Both frail and intermediate frail lead to disability. One key finding from Fried landmark study was the ability to predict mortality with the frailty. This figure taken from her paper clearly describes how non-frail individuals live longer than frail individuals. They studied about 5,000. They studied about 5,000 aged around 60 were assessed for frailty, and then put into 3 groups according to their assessment: non-frailty, intermediate frail, and frail. Subsequently, they were followed for 6 years, and their survival rate was recorded. After 6 years, only 10% of non-frail individuals died. However, 40% of the non-frail individuals died. These are powerful outcomes for our society and managing frailty within the healthcare system. But for me, as an exercise physiologist, 4 of these criteria, walking speed, strength, exhaustion, and physical activity, represent a physical function requiring engagement of muscle. Therefore, physical function can be used as an assessment tool to tease out the role of skeletal muscle in the etiology of frailty. This slide you have seen before. We used the human frailty phenotype to develop mouse frailty phenotype. The word in red identify the approach used to determine exhaustion, weakness, slow walking, and low physical activity. Treadmill test was used to determine exhaustion. Grip strength was used to determine weakness. Road rod was used to determine walking speed, and voluntary wheel running kg was used to determine physical activity. To identify the onset, prevalence, and mortality risk, the research design is critical. We used longitudinal research design for our study. First, we initiated the study with 29 C57 black 6 male mice and 27 for female mice. The 29 and 27 mice were followed across their lifespan until natural death. Second, it was necessary to identify the age at which the frailty cutoff values would be identified. We select 23 months of age for male and 20 months of age for female based on their lifespan. The next critical point centers around our goal to identify the onset of frailty. In order to identify the onset, we decided to test the mice every 3 months, starting at 17 months using our frailty criteria. The blue line represents the age at which we predict the onset of frailty based on our knowledge of muscle function. The fourth point centers around the goal of investigating the prevalence of frailty across the lifespan. The yellow line shows that we predict the prevalence of frailty in both male and female mice to be low in early month and increase with age. Lastly, we want to determine if frailty status at a younger age increase the risk of the death. We anticipate the frail mice identified will die earlier than mice identified as a non-frail mice. Specifically, we anticipate the frail mice will die about 3 to 4 months after being identified as frail, whereas the non-frail mice will live longer. So in order to identify frailty, we used 5 frailty criteria, including walking speed with low drop, strength with grip meter, activity level with voluntary wheel running, body weight and body fat with DEXA and scale, and endurance with treadmill test. This slide shows the timeline of the testing. The 5 criteria were tested over a 7-day period. On day 1, we determined body weight and body fat by DEXA. On day 2, we determined walking speed by load rate. And we also determined strength by grip meter. On day 4, we determined endurance by a treadmill test. From day 4 to day 8, we put the mouse into the activity cage to determine physical activity. The mice are being tested every 3 months. So one way to demonstrate that high body weight has a negative impact is to show statistically that heavy mice at 23 months of age die earlier than the lighter mice. The left panel shows that the heavy mice at 23 months of age, the red line represents the mice in the, the left panel shows that heavy mice at 23 months age die earlier. The red line represents the mice in the top 20% of our group, whereas the blue line represents the bottom 20% of the group, the lightest mice that weight. The right panel shows the fat percent in these same mice. These data confirm our body weight data, showing that mice with greater fat die earlier than the mice that have less fat. We believed this information provides strong rationale to use heavy body weight as a marker of frailty. To identify frailty, there are 5 criteria: grip strength, walking speed, physical activity, endurance, and high body weight. The critical cutoff point for identifying a positive marker for frailty was established by bottom 20% for the performance in grip strength, walking speed, physical activity, endurance, and top 20% of body weight. A mouse was evaluated for these 5 assessments, and if the mouse fell below cutoff value in 3 or more, the mouse was identified as frail. If the mouse fell below the cutoff value in 2, the mouse was identified as pre-frail. This is the survival curve of our mice for both male and female. The x-axis is the lifespan in month, and y-axis is the survival probability in percent. The first mouse died at 23 months of age in female, and the last mouse died at 37 months in male. There is a significant difference between the male and female in lifespan. In our cohort, male mice lived 13% longer than female mice. I already explained how the frailty cutoff values were determined from the 23-month-old mice in male. And the next step is to place each mouse into one of the three groups, frail, pre-frail, or non-frail. On the left of this slide is one way to visualize each mouse and the performance of each mouse on the frailty criteria. The mice were coded A to BB from the best to worst performer for walking speed, strength, endurance, and physical activity. And for body weight is placed from the heaviest to the lightest for the body weight. So after identifying if a mouse was positive for an individual frailty criterion, we summarized the number of the frailty markers each mouse presented with. So this is presented in the right panel. There were 19 non-frail mice in blue, 6 frail mice in gray, and 3 frail mice in black at 23 months of age. For example, BCT identified as frail. Same as male, we identify the frail or pre-frail and non-frail mice at 20 months of age in female, and 5 frail mice was identified, and 5 frail mice were identified, and 17 non-frail mice were identified. We identified the first frail mice at 17 months of age in both male and female. We would like to look at mouse B more closely to identify which assessment are positive markers at 17 months of age. We identified the body weight, walking speed, and endurance were positive markers at 17 months of age. These measures might be critical at 17 months of age to prevent or delay frailty. This slide shows the prevalence of frailty in both male and female mice. First, let me orient it to you graph. On x-axis is age in month, where we assessed each mouse for the frailty criteria. Y-axis is the percent of mice that are frail, pre-frail, and non-frail. As you can see, the onset of frailty occur at 17 months in both male and female, and which is presented as 3.5% and 3.7% of the male and female cohort. The percentage of the mice that are frail increase across the lifespan, such that all the mice are identified as a frail or pre-frail after 32 months of age. As we see an increase in number of mice with frailty and pre-frailty, number of mice identified as a non-frail decreases. We would like to know the sex differences between frail, pre-frail, and non-frail mice. The left panel shows the prevalence of frailty in male and female mice at each time point. There are more frail, pre-frail female mice at 26 months than frail, pre-frail male mice. It seems female mice have more frailty at 26 months of age. However, we normalize to the mean lifespan for each sex because their lifespan was different between male and female. When normalized to the mean lifespan for each sex, no differences were detected. This indicates that the prevalence of frailty in both male and female is similar late. In this graph, the mice are divided into frail, pre-frail, and non-frail, starting at 23 and 20 months of age, and their lifespan were followed until their death. The non-frail mice lived until almost 38 months of age with a mean of 33.8 months for male, 35 months of age with a mean of 30.1 months of female. To determine if the mouse frailty phenotype can predict mortality risk, we followed mice identified as a frail, pre-frail, and non-frail at 23 and 20 months of age across the lifespan. The frail mice had a mean survival age about 27 months, with all the mice dying before 29 months. Using our longitudinal research design and mouse frailty phenotype, we successfully identify the onset, prevalence, are able to predict mortality. This slide shows the survival curves of the frail male and female mice. Frail mice were assessed to determine sex differences on the mortality risk. The frail female mice had the mean survival time of about 27 months, which was not different from the mean survival time of about 29 months in frail male mice. There was also no difference between mortality rate of frail male and female mice when evaluated by survivor following the frailty assessment. So using this approach, we discovered that the pre-frail mice were already showing functional difference at early age compared to the non-frail mice. The non-frail mice are in the blue bar, and the frail, pre-frail are grouped together and represented in the dark gray bar for body weight, walking speed, and endurance. First panel show body weight. The frail mice weight significantly greater than the non-frail in blue. In the next panel, the walking speed is highlighted. As you can see, walking speed was different between frail, pre-frail, and non-frail mice. The bottom panel highlighted the treadmill test for endurance, and again, there was tendency for difference between frail, pre-frail, and non-frail mice. In fact, the time for endurance was 17% less in frail, pre-frail mice compared to the frail mice at 23 months. Here is a summary. You can look at it. And now I would be happy to take your question. Thank you.
Thank you, Dr. Kwok. It was a very insightful presentation. I appreciate your presentation one more time. Okay, so we're going to have questions from the floor. Just to show us a hand if you have any questions. So, okay, so Dr. Song.
영어로 해야 되는 거죠? 네. Okay, thank you for the great talk, Professor Kwok. Interesting talk because we've been working also in the area of frailty over the years, but at any conference we didn't find a good animal model of frailty, but you demonstrate quite well with your study. So I'm wondering, is there any other lab actually conform your frailty data and survival curve, because you have about 30 animals, and it looks like we have a variety of mouse species and also cohorts. So that's the first question, and then maybe in the same context of the question is that how actually would you apply, if there is a really frail animal of this mouse model, then what would be the application? Is there any other work had been done looking at this frailty phenotype in real study, maybe the exercise science study as well?
Okay.
Thank you.
Thank you. Thank you for your question. And your first question would be how you can validate your survival curve for such a small number of the animals. So basically, NIH actually provide the big husbandry for survival curve, and for this actually the species, and actually our species live a little bit longer than their husbandry. but maybe there is a couple of reasons, but we are quite not sure. Maybe husbandry is really good for our facility, or might be we put the male and female together, so the female's menstruation cycle will be running, so that maybe they can survive a little bit longer or shorter. So we are quite not sure. And also, the second question will be another lab maybe provide this kind of the information using the animal model. So basically, Hubbard also focused on the bone frailty, and basically frailty phenotype. Actually, in the frailty world, there are actually the major two type of the frailty assessment tool. The first one is frailty phenotype, and second one is frailty index. So actually, one of the scientists compare both assessment tools, and they're not much different. And also, because I'm an exercise physiologist and I'm working in the division of sports science, so I'm more focused on the muscle related. So that's why I'm really interested in this physical function to use assessment tools. So I'm not sure, but I hope that this answer will be helpful.
Yeah, thank you very much. Another questions? Okay, I have a quick question, very small question. Maybe I missed it, but can I ask you what species of mice were utilized?
C57 Black 6 is mostly widely used.
Yes, okay. Then maybe there might be significant difference, you know, between species by species.
Yes.
Yes, so would you able to draw the conclusion out of a one species study?
Actually, as you can see in my the graph, actually there is actually I tested from this actually the 14 months to the 38 months. It's about 2 years, right? So only for taking the data for 2 years. So might be this is very hard study to conduct. I hope that if I have enough money to keep the mice, and maybe I will try to test for Babishi mouse or nude mouse or short-lived mice, but at this moment, I'm not sure.
That's the correct question. Thank you.
Thank you.
Okay, so maybe he was so perfect, so there are not many questions out of the floor. Let's give him big applause.
Thank you very much.
We're gonna have a coffee break short. Just we're gonna start again 4:10. Please remember 4:10. We're gonna start again.
이러면 훨씬 좀 나을 거야. 아.
In this video, you will learn
Press the modified test you are conducting on an individual.
video picks up where the B tracks test to the testing screen. So step onto the plate 20-second trials that begin and end viability. Support buttons at the bottom of
Tested center of pressure. To the right, weight distribution the part and hands on the third trial is complete. CT SIB with 3 descriptive metric of the screen.
Wires all over our bodies and really kind of seeing where performance can be taken to the next level.
And how my lungs work.
Good job.
Within a few minutes, we're seeing changes.
Small
I'm monitoring and get a better dynamic cross of your averages, for instance.
Selectivation, if we can manipulate that some.
Physical performance is an ergonomic handheld rest feedback and training implant and evaluated using the.
But what is the reason we need a training device and to focus on breathing failed when the lungs is very similar, with humidity drips out of the device. With the app, the feedback looks a little different. On this slide, I also want to show you
without resistance. Thanks to the IDIAG P100's automated assessments, individual weaknesses can be detected.
우리 이제 땀 좀 흘려볼까?
날 좋아한다고
언젠가 우리 같이 뛸 수 있도록. Let's sweat, be happy. 포카리 스웨트.
Ladies and gentlemen, as we are about to begin resume our current session, so please be seated, and we'll start in 1 minute. Thank you. So we will start the next session, the current session. So please be seated, and please thank you for your kind cooperation and attention.
Right, let's resume the session. I want to introduce the next speaker, Dr. Seung-Yong Lee from Midwestern University, Glendale. He finished his bachelor's degree at Dankook University, master's degree at University of Kentucky, and PhD at the University of Texas at Arlington. And after working as a postdoctoral research fellow at Johns Hopkins University School of Medicine and University of Toledo, now he is currently working as an assistant professor at Midwestern University. Today, he's going to talk about aerobic exercise and bone metabolism, and he's going to present by recorded video. After his presentation, we will have an online Q&A time. Thank you.
Good afternoon, everyone. First of all, I will thank the Scientific Program Committee for giving me this great opportunity. I'm very glad and excited about having this presentation, which is entitled The Aerobic Exercise and Bone Metabolism, the Role of Bone-Associated Skeletal Nerves. As a background information, the osteoporosis is the bone diseases in which the bone density and quality are reduced, as you can see in the images of human and rat osteoporotic bones. So over 200 million population worldwide have osteoporosis, and 25% of all the adult population is osteoporosis, which suggests that this is common age-associated bone diseases and reducing the quality of their life. So the main cause of osteoporosis is the imbalance of bone-removing cells, osteoclast, and bone-forming cells, the osteoblast. If the osteoblast activity is less than osteoclast, we will lose our bone volume. During this process, blood vessel plays a significant role in supplying oxygen, nutrients, and precursor cells, and or other factors to that area. The changes in bone metabolism according to the functions of these blood vessels have already been reported throughout many studies. However, insufficient information still exists as to whether bone-associated skeletal nerves influence bone metabolism. The recent paper demonstrated the reduced periosteal nerve fiber numbers and density are associated with the age-related bone loss. They observed the highest density of CGRP positive sensory nerves and TH positive sympathetic nerves and CD31 positive blood vessels in the layer of the periosteum in young animals. However, both CGRP positive and TH positive fibers were decreased in aged animals up to 50%, and there was a modest reduction in CD31 positive blood vessels. Therefore, as a consequence of aging, This suggests a relationship to decreased nerve fiber number and or density, and possibly associated with age-related declines in bone volume and metabolism. Then how are the nerves in the bone spatially distributed, and what functions do they perform? Just as nerves are connected throughout the body, many nerves are distributed in the skeletal systems as well. So most basically, the nerve system delivered to the skeletal system is, as you all know already, the peripheral nerve system. So these peripheral nerves plays a role in conveying information between the central nerve system and bone tissue. As shown in the figure, these neurons in peripheral nerves are located in sensory and autonomic nerves that propagate the peripheral nerve axons to the target bone tissue through a bundle of nerves like this. If you look at the following table, you can see that the axons distributed in the skeletons are classified into size, myelinations, and functional classes. These various nerve fibers are distributed in the skeletons, of which it is reported that the small or medium-sized, either myelinated or unmyelinated nerve fibers are mainly distributed in bone tissue. As a result of checking with these morphological factors, it has been reported that most of nerve fibers distributed in bone tissue are mainly the sensory nerves that expresses this tropomyosin receptor kinase A, which is called TrkA. As shown in this figure and confocal microscopic images, it can be seen that the main nerves that passes through the cortical bone and distribute in the periosteum and bone marrow spaces are the sensory nerves that marked in the green here in these figures. And the sympathetic nerves are also distributed, but they usually maintain their patterns related to the blood vessels in bone tissue. Based on these previous studies, many studies recently have been conducted to determine the effects of skeletal nerves on bone development, fracture or bone defect healing, and bone losses related to the neuropathic diseases. Among these studies, let's take a look at the studies dealing with the sensory nerves that expresses this tropomyosin receptor kinase A, which is the main components of bone nerves, and the mechanisms of NGF signaling, a nerve growth factor that works closely with these receptors. First, the effects of nerve growth factor, NGF, and its receptor TrkA signaling mechanisms on bone growth in newborn mice was reported. When you see this figure, a very high amount of nerve growth factor was expressed in the ossification center of the growing mouse femur during the endochondral ossification process. This nerve growth factor was shown to be expressed in osterix, which is an osteochondral progenitor marker. The following figure is the phenotype of genetic deletions of NGF from the NGF-TrkA signaling pathway. As you can see, a significantly short femur length was measured in mice with NGF deletions. Similarly, when TrkA was removed from the NGF-TrkA mechanisms, it was confirmed that there were decreased sensory nerve density and reduced bone volume and size. Therefore, this study showed that inhibiting the NGF-TrkA signaling mechanisms during bone growth that suppresses normal bone development, suggesting that this NGF-TrkA signaling coordinates neurostimulations and bone development. This another study is representing the effects of the NGF-TrkA signaling mechanisms on the recovery of ulnar stress fractures. This micro-CT reconstruction images showed a normal timeline for stress fracture healing for 2 weeks. As you can see here, trabecular bone formation at the fracture site was first observed 7 days after fracture, and the rigid bony callus formation was observed, and the size of this callus were the largest at 14 days after the fracture. Next, in the same paper, it shows how NGF expression changes during the normal process of 2-week stress fracture healing process. A slight amount of NGF was expressed in the ulna before injury, but 3 to 7 days after the fracture, in other words, just before the formation of the bony callus, most cells in the fracture area showed a positive expressions for NGF. On the 14 days after the fracture, which is the strongest and the largest callus formation period, the NGF expression was mostly expressed in bone lining cells, which is osteoblast. As a result of analyzing the nerve regeneration after fracture, similar to NGF expression, it was shown that the nerve regeneration predominantly in bony callus and the periosteum from 3 to 7 days after fracture, and the frequency of nerve were decreased on the 14 days post-injury. After that, we examined the effects of TrkA suppressions and stress fracture healing. As shown in the micro-CT data, new bone formation was significantly reduced in the group that deleted TrkA, and this phenomenon was closely related to the significantly reduced skeletal nerve fiber density. Therefore, inhibiting the TrkA catalytic activity in the skeletal sensory nerve during stress fracture healing resulted in a significant reductions in skeletal nerve regeneration and a delay in fracture treatment. Since this phenomenon and the role of these NGF TrkA signaling mechanisms were also evident in treatment after calvareal bone defect, so bone-associated skeletal nerves appear to have a great influence on bone development and regeneration. Then let's check the effects of aerobic exercise on the peripheral nerve system. In general, aerobic exercise is reported to relieve symptoms of acute pain, which is closely related to the sensory nerves. In addition, the prevention of neurological diseases such as anti-inflammatory effects, cardiovascular diseases, dementia, and the Parkinson's disease through exercise has been reported previously. And recent studies have shown that the aerobic exercise is effective in promoting peripheral nerve regeneration and preventing this peripheral neuropathy. This published study demonstrated that the aerobic exercise prevents peripheral neuropathy in mice caused by the chemotherapy agents paclitaxel. All the mice performed a treadmill running exercise 7 times a week with low intensity for 4 weeks. As shown in the figure, nerve fiber density in the epidermis of the foot are evenly distributed in mice that have not taken anti-cancer drugs. However, the nerve density was significantly reduced in mice administered with chemotherapy drugs, but the aerobic exercise training prevents this peripheral neuropathy progressions. So another study reported that the aerobic exercise promotes nerve regeneration after damage to the median nerve of forearm. In the exercise mode, mice performed treadmill running exercise 5 times a week and for 6 weeks of low intensity. If you look at the contents, as you can see that the nerve regeneration was promoted as the amount of axonal density and their size increased in the group that performed the exercise shown in the middle. This was significantly different from the group who did not exercise, and it was regenerated to a level almost similar to that of the nerve that was not injured. So the authors explained that the cause of this promoting the peripheral nerve regeneration is the effects of increased glial-derived neurotrophic factors, brain-derived neurotrophic factors, and insulin-like growth factor 1 in the body through the exercise. As such, aerobic exercise appears to have positive effect on the peripheral nerve system, but so far it has not been revealed how aerobic exercise will affect bone-associated skeletal nerves. If so, will aerobic exercise control the density of skeletal nerves and affect bone metabolism during aging process? To confirm the effectiveness of aerobic exercise that positively affects bone-associated skeletal nerves and bone metabolism in middle-aged, we used 14-month-old C57 Black 6 mice and all mice performed a high-intensity treadmill exercise with 18 meters per minute for 30 minutes per day for 8 weeks, which equivalent to the 85% of VO2 max. After the exercise intervention, bone mineral density and bone mineral contents were tested using DEXA scanner, and the characteristics of trabecular bones were analyzed by using micro-CT. Bone-associated skeletal nerves were imaged and analyzed by using immunofluorescence staining and confocal microscope. Further, we used microarray data obtained from the publicly available gene expression omnibus database to reanalyze the expression profiles of microRNA in femora following aerobic exercise. First, we look at the effects of high-intensity exercise on the femoral bone metabolism of middle-aged mice. As a result of DEXA analysis, it was confirmed that the total area of the femur, bone mineral density, and bone mineral contents increased significantly after exercise. This micro-CT image represents the area of interest in the distal femur, which is the secondary spongiosa of the distal metaphysis. Also, as shown in the representative images between the two groups, it can be seen that there are higher distal femoral trabecular bone volume in the exercise group. This was proved by significantly increased bone volume and the fractional bone volume as shown in the panel G and H. The increased bone volume was mainly due to the augmented trabecular numbers. So similar to the femur, the comparable result was derived in the tibia. First, although the tibial area did not differ, the bone mineral density and bone mineral content values of the aerobic exercise group were 20% and 35% higher than the non-exercise group respectively, which were statistically significant. Also, very meaningful differences in proximal tibial trabecular bone microarchitecture were observed following the aerobic exercise as shown in the representative images. So trabecular bone microarchitecture in the proximal tibia revealed that the trabecular bone volume per total volume, and trabecular number of the aerobic exercise group were higher than those of the non-exercise group. Therefore, these data suggest that the volume of the trabecular bone increases in both the femur and tibia when high-intensity treadmill aerobic exercise is performed for 8 weeks. Next, we determine the effects of 8 weeks of aerobic exercise protocol on bone-associated skeletal nerve fibers in the distal femoral and the proximal tibial periostea. As you can clearly see, for both distal femoral and proximal tibial periosteum, nerve fiber density was greater in mice of the exercise group compared to the non-exercise group. The density of beta-tubulin positive nerve fiber was increased by 99% in the distal femur and 88% in the proximal tibial periosteum following aerobic exercise. Therefore, these findings suggest that the aerobic exercise training program effectively increased skeletal nerve density in the periosteum of the distal femur and the proximal tibia. From this point, we were curious about the associations between skeletal nerve fibers and trabecular bone volume of the distal femoral and the proximal tibia, so that they were analyzed using bivariate correlation analysis. Interestingly, the significant correlations were observed between the periosteal nerve fiber density and trabecular bone volume in the distal femora in mice of the exercise group, which is in orange color, while there is no correlation observed in the non-exercise group in blue color. Although not statistically significant, a high correlation was observed between skeletal nerve fiber density and trabecular bone volume in the proximal tibia for the aerobic exercise training group, while these variables were weakly associated in the non-exercise group, which is in blue. So these data suggest that improved trabecular bone following aerobic exercise training could have been achieved via the increased nerve innervation. Lastly, we assessed these potential upstream mediators of osteogenesis and neurogenesis in mice femora by using microarray dataset reanalysis. So re-examination of the microarray dataset shown in A revealed that a total of 191 out of 1900 microRNAs were differentially expressed significantly between the non-exercise and aerobic exercise training groups. So out of 191 microRNAs, 91 microRNAs were overexpressed, while 100 microRNAs were down-expressed with aerobic exercise training. Particularly, 16 microRNAs that are related to osteogenic and neurogenic regulations were selected and shown in panel B among the differentially expressed microRNAs. This appears to involve these microRNA 130B-5P, for example. The overexpression of this microRNA induces neural progenitor cells proliferations and attenuates neuronal cell apoptosis in the central nervous systems. Similarly, the microRNA 130A-3P overexpression promotes the vascular endothelial growth factor receptor 2 expression in the sensory dorsal root ganglia and regulates the peripheral nerve system by stimulating axonal growth. The overexpression of microRNA 130A-3P also regulates bone metabolism, which in turn increases osteogenic differentiation of adipose-derived stem cells by enhancing the Wnt beta-catenin signaling pathway. Even though there are potential upstream mediators of osteogenesis and neurogenesis, the exact physiologically important downstream gene and molecular mechanisms that stimulate osteogenesis and neurogenesis in the bone remains unknown, and they are the really great subject of future study. Finally, to summarize this presentation, bone-associated skeletal nerves are very closely related to bone development, fracture repair, and bone loss because of the peripheral neuropathy. In addition, the proper aerobic exercise promotes this regeneration of peripheral nerves and relieves disease-related peripheral neuropathy. Therefore, based on the background literatures and our recent data, aerobic exercise is believed to be able to activate the skeletal nerve stimulations and control this bone growth and regenerations. However, since the exact mechanisms has not yet been explained, I think how skeletal nerve stimulation through aerobic exercise affects bone remodeling cells is a very interesting research topic that has yet to be solved. Thank you very much for your attentions, and any questions will be welcomed. Thank you.
All right, we will have online Q&A time. Dr. Lee, do you hear us?
안녕하세요, 이승입니다. Can you hear me?
Do we have any question to Dr. Lee? Dr. Lee, first of all, thank you for your insightful presentation. Thank you.
Yeah, thank you. First of all, I'd like to thank the academic committee for inviting me to present our data in the International Conference of the KSEP. Thank you.
All right, thank you. Do we have any question on the floor? All right.
Thank you for your presentation. I wanted to ask you about the high-intensity aerobic exercise that you presented in your presentation. I wanted to know if there is any study that compare different intensity of exercise on bone nerves, and if there's only high-intensity exercise stimulates the bone nerves, I wanted to know that, do you think that in real life, elderly can also perform high intensity and get benefit of the exercise? Yeah, that's my question.
Thank you. That's a very great question, I think. So I would say there are so many literatures out there already being published about the positive effects of exercise on the peripheral nerve fibers in different organ systems, like the skins or medial nerve in the forearms. But this, I would highlight that this study has been, this is like first study in the world actually to demonstrate these changes in bone, skeletal nerve fibers following the exercise training. So, this is, that's why I'm very careful to say that, but my assumptions and then my hypothesis is that, but there should be some degrees of changes in nerve fiber density with the other types of exercise or other intensity or different modes of exercise as well. As long as it has above the threshold, so that stimulates actual bone, the nerve fibers. Then eventually we will promote the bone metabolism and then bone regeneration as well. But again, however, this is also, we definitely need a follow-up study to find out exact mechanisms behind these situations. So that way we have to find out better mechanisms and effective the exercise training modes and then intensity. But in person, elderly person per se, I really cannot say that because this is really early time point of study. So we have to have really great further studies. Thank you.
Do we have a microphone? Dr. Uk Song?
Yes. I'm Song from Seoul National University. Thank you for your talk and very nice work. Maybe I missed your point in your presentation. Pretty much your data about trabecular bone, is that right? But
yes, for now, yes.
Yeah, but the most of the more proportional bone is kind of not the trabecular one. Another one is more the high density one, a cortical bone, right?
So yes, so the periosteum is actually the membrane of the outer surface of the bone, the long bones. But where we measure in the periosteum of the trabecular area is actually little outside of the trabecular area. So we also have the cortical bone data, and there's also significantly beneficial effects on the exercise in the correlation with the nerve fiber density, but that what I didn't really put in there.
Okay, because I was wondering, there is two major, the cortical and trabecular bones, so it seems to be more differential response in terms of your work and looking at the mechanism of action. So I was wondering if the same effect in the cortical bone area, because it seems to be a little bit different response to exercise. So that was my question. And then maybe for the further study, are you planning to do the resistance exercise on the same the study plan, what you showed today? Because the aerobic is quite effective, seems like the muscle nerve, but why not the resistant type of exercise? But still, there's a limitation in the rodent model, so I'd like to hear your further study plan. Thank you.
Okay, thank you. So the first one, there's a cortical bone effect on the exercise and then nerve correlations as well. But there's a little bit different effects compared to the trabecular bone. So I should present that in this presentation. But when you can refer to our new publications, so you can check out the cortical bone changes. And also for the next step, I actually plan on doing some combined exercise model first. So the aerobic exercise and then the resistance exercise combinations together to if that is effective in the bone nerve fibers too. Not only the nerve fibers with the different types of exercise, but I'd like to do the mechanistic studies, what is actual molecular and cellular and molecular pathway of the mechanisms behind the situations. Thank you for asking.
Thank you very much.
All right, thank you, Dr. Lee. Thank you. Then now let's move. Thank you. Let's move on to the next speaker. Okay, we'll have 5 minutes break time once again.
자, 안내 말씀드리겠습니다. 원래 저희 룸 1에서 지금 현재 조지 리아 루아스 캐롤린스카 인스티튜트에 있는 교수님께서 원래 발표하시기로 되어 있으셨으나 좀 위급한 그런 상황에 계셔서 지금 접속이 안 되시는 것 같아요. 그래서 지금 죄송하지만 지금 조지 루아스 교수님은 다음 기회에 또 기회가 되면 저희가 지금 위원장님께서 지금 뭔가 지금 답이 또 오고 계신 것 같아요. 한 2, 3분만 조금만 더 기다려 보고 지금 줌으로 지금 가능하면 렉처를 하도록 하겠습니다. 좀 2, 3분만 더 기다려 보겠습니다. 죄송합니다. 그리고 기다리는 중에 또 다른 안내 말씀드리겠습니다. 5시부터는 이제 저 이 포스터 세션이 시작된다고 지금 프로그램에 써 있는데요. 이 포스터 세션은 온라인으로도 시청 가능, 유튜브 온라인으로 시청 가능하시고요. 여기 현재 대면으로 참여하고 계시는 분들은 저 뒤편에 룸 1 뒤편에 또 이 포스터 세션을 시청할 수 있게 저희가 또 셋업을 해 놓았습니다. 5시부터 6시까지는 저희가 6시에 시작하는 저희 키노트 렉처죠. 오늘의 키노트 렉처로서 저희 김창주 교수님께서 거의 1시간 동안 이제 렉처를 해주시는데 그 중에 저희 만찬을 저녁 식사를 하시면서 저희가 그 렉처를 듣기로 되어 있습니다. 그렇기 때문에 5시부터 6시까지는 여기 자리를 저녁 먹는 준비를 해야 되기 때문에 이 룸 1에서 잠시 나가 주셨다가 그리고 6시부터 저녁 식사를 먹겠다고 등록하신 분들은 6시에 다시 여기에 오셔서 김창주 교수님의 렉처를 들어주시면 되겠습니다. 더 질문 있으신 분들은 언제든지 앞으로 나오셔서 질문해 주시면 감사하겠습니다. 안내 말씀드리겠습니다. 죄송하지만 저희 그 조지 루아스 교수님께서 지금 저 인터넷 접속이 지금 대기하고 계시는데 인터넷 접속이 계속 불가하고 안 된다라고 말씀하셔서 아쉽지만 다음 기회에 루아스 교수님의 렉처를 듣도록 하겠습니다. 지금까지 고생해주신 저희 좌장님들께 먼저 박수 한번 부탁드립니다. 그리고 지금부터 6시까지는 방금 말씀드렸듯이 이 룸 1에서 6시부터 시작하는 김창규 교수님의 렉처를 위해 또 만찬 준비가 되어 있어서 만찬 준비를 하는 중에는 여기 룸 1을 좀 비워주셔야 됩니다. 그래서 룸 1을 좀 비워주셨다가 만찬을 참여하시는 분들은 6시에 다시 여기서 뵙도록 하겠습니다. 감사합니다.
학부는 성균관대에서 하고 석사, 박사 후라고 미국에서.
성대만 대학 학부만 나왔다는 얘기구나. 그지? 잘했어. 이거 놓을 자리가 없잖아. 이렇게 여기 있는데 이거 키면 돼 내가?
네.
이거 막 울리네. 말하면 안 되겠네.
마이크 조금 뒤로 뺄까요?
나중에는 이제 땡겨가 하더라도 이게 안 비치네. 그러면
지금은 저쪽에서 조절하라.
그럼 이게 낫나? 이게 보이는지 안 보이는지 그러니까 한번 떼어줘. 이게 잘 보이는지 이게 이렇게 놓고 튼닝 페이퍼를 써야 되거든. 준비